Yes, ma'am. So what we did in the last class, would anyone like to tell? Can anyone recollect what we did in the last class?
Ma'am, we started with
Yes.
overfitting and underfitting.
Very good.
Underfitting occurs when the model didn't learn properly to understand the patterns.
Excellent, sir.
Whereas overfitting occurs when the model learns uh, is weighs certain parameters and take biased decision based on those parameters.
Hmm.
Underfitting occurs due to poor data or high dimensional data with poor density, or the model hasn't sufficiently trained enough.
Yeah, when the model has not learned enough. Overfitting is when the model has learned specific details. Yeah.
For
Then
under
we saw. Yeah. Go on.
uh, for underfitting, we can um, like train the model properly or provide a good amount of data. For overfitting, we can do certain methods like early stopping, dropout method, where we can randomly uh, disconnect certain neurons in it. And one
Yeah.
more thing is batch normalization. So the weights will be normalized across all the neurons. Then we moved on to artificial neurons.
So these things we can tell it as regularization methods.
Okay.
Yeah. Then artificial neurons.
Yes, ma'am. Artificial neurons, they represent as logic expressions where it takes weight inputs and take decisions, and it can form
Fantastic.
interconnections between other artificial neurons.
And we saw a model, simplest model called perceptron.
Yes, ma'am.
Yeah. Fantastic. Anyone would like to add to this? Okay, this is what we have pretty much covered in the last class, and we have started learning about neural networks. So, in this class, what we will do is that we will learn two things. One, we will learn about the learning and reasoning in machine learning, and the other thing, we will learn about classifiers in this class. So, we will learn about learning and reasoning, and also we will, if time permits, we will also learn about different types of classifiers. So, learning. So suppose if you have some statements, you believe that statements to be true, then how do you represent those statements? If the statements are true, how do you discover new statements? How to believe the new statements, whether it is true or not? So all these are the questions which will come in the learning. Learning is you are learning a new statement. How do you represent a new statement in machine learning? How to discover new statements? How to believe the new statements? How to decide if the new statements are true or not? All those things will be covered. So suppose if you are imagine that you have you know some people and you are offering a piece of information to that people. So how they will make a judgment about how to trust that new information or not? Most of the time when some information is given to a person, that can be a truth, partial truth, misunderstanding, misrepresentation, even lies. So how to take a good decision on what to believe and what not to believe? Right from ancient Greeks philosophers and logicians, they have been developing a body of knowledge that attempts to provide a formal structure for deciding the reliability of information. So they have developed a formal knowledge. When it comes to machine learning, we have tools of logical thinking. So these tools form the foundations of machines to learn. So what the machine would do when a new information comes, it will try to integrate this new information with what it has already learned using these tools of logical thinking. Because if you look at machines, unlike human beings, they process information based on their life experiences or gut feeling or common sense. But computer does not have common sense or gut feeling or life experience to explicitly use those informations. So it needs to use formal rules to process information and to draw conclusions from the information. So human beings do with life experiences, but here everything is based on rules. So to process information, it needs rules. To learn information, it needs rules. And to draw conclusion from the information, it needs rules. So, so this is all essentially learning, processing information, drawing conclusion. These are all learning for the mission. Whether it is a mission or a human being, learning is a complicated process. So let's break down the process of learning. So the learning process can be divided into three steps. The first step is representation. The second step is evaluation. The third step is optimization. So machines learn using the formal rules, and through these three process, machine learns. One is representation of the data, second evaluation of the data, third is optimization of the data. So using these three rules, machine learns. So first we will see about representation. So do you have any questions? Is it clear?
Yes, ma'am.
Okay. So what is representation? Representation means it describes what sort of things it is capable of knowing. So I can say that representation can happen in three forms. One is what is saved, what is learned, and what is remembered. So what data is saved, what data is learned, and what data is remembered. So representation can happen in both inside the learner and the input data. So representation can happen in both the things. In machine learning, if you take representation can take place in inside an architecture and in algorithms. So in machine learning, representation is nothing but in an architecture for organizing the parameters. Algorithms to modify and interpret those parameters. So we saw that representation is describing what things we know, and it can happen in it can place limits on what is saved, what is learned, and what is remembered. Representation takes place both inside the learner and the data which goes inside the input. And what is usually representation in a machine learning algorithm is in its architecture for organizing the input parameters, and in the algorithm for modifying and interpreting those parameters. So let's take an example and then we'll go forward. In the last class, we learned what is perceptron. Perceptron is a simplest type of neural network. It consists of an input layer, output neuron, and it has an activation function. It has an activation function which produces the output whether it is 0 or 1. It has an input layer which takes the weighted inputs and gives to the activation function, and it produces an output based on the outcome of the activation function. So we know that we will adjust the weights of the training in the perceptron so that it can draw a straight line to classify a data. So perceptron classifies data using a straight line. So what does the representation means here? The perceptron represents a decision boundary using its weights. It is nothing but the decision boundary is nothing but the line which separates the two classes. Suppose if you have two classes like this, the perceptron has a straight line. The straight line is nothing but the decision boundary which separates these two classes, but it can classify only using a straight line. It cannot, it's a linear algorithm, so it cannot have curved lines. It can only have straight line. So if the data is linearly separable, then perceptron is useful. If the data is not linearly separable, then how much ever training you use, no matter how much training is it receives, it cannot be successful because it requires a curved boundary. So I can say that perceptron can only learn straight line boundaries. If I say like that, perceptron can only learn straight line, I'm meaning that it has very limited representational power. It can represent only straight line. So it has limited representation power. So what is representational power? Representational power is nothing but referring that how complex a function or a model can learn. It can learn only a straight line. So it has limited powers. So what is the implication? Suppose if you want to have a nonlinear boundary, then we need to use multi-layer perceptrons. We need to use multi-layer perceptrons with more hidden layers, or you need to use some neural network with nonlinear activation functions. So a system cannot represent, it cannot know. So what a system cannot represent, it cannot know. So whatever it represents, it will know. So sometimes, so an algorithm with its information, with its way of representing information, along with the particular set of values, we call them as models. Is it clear? So perceptron has limited representational power. So in order to classify a nonlinear boundary, then we need advanced algorithms like multi-layer perceptron. So a single layer perceptron is capable of classifying only with a straight line. So it has limited representational power. So we need to have algorithms which have more representational powers. That is either by using multi-layer perceptron or a neural network with nonlinear activation function. So the way of representing the information along with a set of parameters, you can call an algorithm as a model. So suppose it doesn't mean that always having more power means it's more benefit. previously in the previous class, we saw that when it has a curvy boundary, it overfits. So sometimes more power is also not useful. So we need to have an appropriate power. So the trick of teaching the power representation is we have to start slowly and then we have to build the model from simple to complex. So another example for that one is neural network. We will see about this neural networks in detail in the upcoming classes. So but I will briefly tell how it learns from a simple to a complex process. So how it learns means, so the first layer consists of edges and textures. The second layer, not the second, you can consider as a middle layer, consists of it can recognize shapes like lines, circles, and so on. The last layer can recognize objects like faces, cars, cats, etc. So if you look at how it is learning, so we said that to know the limit representational power, we need to build the algorithm from simple to complex. So the first layer contains simple features like edges, textures. The middle layer contains medium level features like shapes such as lines, circles, corners, etc. So the last layer contains specific features like faces, cars, cats, dogs, etc. So we are learning from simple features to complex features. Thereby, we are increasing the representational power of the algorithm. So is it clear? So what is more important is that we need to choose the right algorithm with the right representation for a given problem. So that is important. We know why we need to choose a right algorithm, but why we need to choose a right representation is that so that we can know what a model can, why right representation. So why we need to have a right representation is that because we know what a model can learn, how efficiently it can learn, and whether the learning is even possible. So these answers can be answered through the right representation. So we need human judgment to select the right algorithm. So we need right algorithm as well as right representation is needed. So to choose the right algorithm, we need human judgment because a machine learning is not capable of automatically choosing the best approach. So human has to interpret it. So first of all, we need to understand the data and the task at the hand to pick the right algorithm with the right level of power. So if the model is too simple, what will happen? If the model is too simple, it may not capture all the complexities in the data. So it can lead, if it is not understanding a lot of complexities, then it can lead to underfitting. Suppose if the model is too complex, it can learn unnecessary details and it can fail to generalize. Then it can lead to overfitting. So the goal here is to balance the complexity and the efficiency so that the model can effectively learn. So the first thing is that we need to use human judgment in selecting the right algorithm. So how do we do that? We inspect the data and we understand the task at the hand, and then we pick the algorithm with the right representational power so that we can balance complexity and efficiency. So the second thing what we need to do is that we need to match the representation with the problem. So the representation must match the problem. Because different data needs different representations. Suppose we have two data cluster, which is separated by a curvy boundary. So it needs a curvy model which can represent curves. We cannot use a linear model like perceptron to separate the clusters using the curves. We will fail in that situation. So we need to choose a model that can represent curves. So based on the data, we have to choose the representation. So the third thing is the hierarchy of the system. So initially, the first hierarchy is what can be represented. So what can be represented is that the system representation determines what it can describe and remember in a theory. Second thing, we need to know what can be learned. All that is represented cannot be learned. So some things that is represented cannot be learned. Some things are representable but still cannot be learned. So we need to know what can be learned. The third thing is what can be learned practically. Because sometimes things can be learned, but only with unlimited time and resources we can learn certain things. If you lack computational power or storage or time, learning can be impractical. So we need to know what can be learned in practice. The fourth thing is what can be learned efficiently. Finally, like even though there is a problem in learning in practice, some representations we can learn very slowly and with inefficient means. We can only focus on the problems that can be learned with the available resources. So what can be learned efficiently is important. So the hierarchy is what can be represented, what can be learned, what can be learned practically, what can be learned efficiently. So this is the hierarchy in what a system can learn. This hierarchy will help us decide what is possible and what is practical in machine learning. Suppose if you have limited memory, we must have a trade-off between what we can store and what we can represent. So we need to know about the information limits and representation. There needs to be a trade-off between what can be stored and what can be represented. And finally, we need to choose the right algorithm, architecture, and representation. So choosing the right architecture and parameter settings can limit us from unnecessary complexity and speeding up of things. So the main summary here is that we need to choose the right algorithm with right representation because it is crucial for effective learning. We cannot represent what we cannot learn. So there are problems which are impossible to learn, which are impractical to learn, some are practical to learn. So what we need to do is that we need to make good design choices with these tips, which can help balance both power and efficiency. So this can allow the models learn just enough without overcomplicating things. Is it clear? So this is what we learned in representation. So in representation, so we learned the definition of representation, and we saw how in machine learning we represent the data. And we took the example of a linear system called perceptron, and we saw how it is possible to classify the data, how it is not possible to classify the data with using the representational power. And then we understood what is a model, and we need to train the model from simple to complex. So we took an example of neural network, and we learned how it learns features from a simple to complex in neural network. Then we saw why we need a right representation, and what are the steps involved in providing the right representation. So now we will go on to the next step in the learning, which is called as evaluation. So learning is a continuous process. So what is evaluation? Anyone would like to tell upon it? We have touched upon this before also. What is evaluation? So evaluation is a process of checking how well a system can perform by comparing its actual response to the expected or a desired response. So let's break it down. So you have your input or a stimulus. It is the input which we give to the system. Second, we have a system response. So system response is nothing but the output. So based on the internal logic of the system, it will produce an output. So a system has an input, a system has an output, and it also has an expected response. So expected response is nothing but the ground truth. So what is the predefined correct answer for what we have expected for? And the fourth thing is comparison. So comparison means evaluation. So what is comparison? What are we comparing? We are comparing the system response with the ground truth. So we are comparing the system response with the expected response. If the system response is close to the expected response, we evaluate that the model is performing well. If it is not performing well, then we need to retrain or refine our parameter. So let's take some practical example. So imagine we have our input, we have our output, we have our ground truth, we have our comparison. So let's imagine we have a classification problem. In the classification problem, we are classifying dogs and cats. So if you have an image of a cat, but the system produces the label, output label of a dog. But what is the ground truth? The ground truth is the cat label. So what has happened? There is a mismatch, or there is a mistake made in classifying the output of the cat. So then we can say the accuracy is low. The model accuracy is low. Let's take a medical example. So you have an X-ray of a lung. So by seeing the output of the system says there is no disease, but the ground truth says it has pneumonia which is present. Now you can tell that the AI had made a mistake in detecting the pneumonia. So we need to improve it. So this is the evaluation which we receive. There can be another example in self-driving cars. So there is a traffic light which shows red as an input. So when the traffic light is red, the car should stop. That is expected, but the car keeps moving. That is the system's output. But what is the ground rule? The car should stop. So this is a critical error which must be fixed for the safety. So these are the different examples of evaluation. Now, do you understand? So evaluation means checking how well our model performs. So checking with what? Checking with the ground truth or an expected response. So the system response will be, the output will be checked with the ground truth or compared with the ground truth for the purpose of evaluation. That will tell us uh, how well our model performs. So these are some examples of AI in three different tasks. So usually in machine learning, there is a to quantify the process, there is a numerical score. So this numerical score is otherwise called as a error score or a loss score, or simply an error or a loss. So what this error score or a loss score does is that it captures how close our algorithm has come to what we wanted. So it is calculating the difference between the two, between the expected outcome and the system's actual outcome. So it will calculate the difference between the two and it will quantify with a score called as error score or a loss score. So there are so many ways of evaluation. Sometimes we can, in the previous examples, we have seen uh, some evaluation metrics called accuracy, precision. If you could recollect in our earlier classes, we have studied all these parameters, evaluation parameters. So we can use these parameters. There is a lot of machine learning libraries which offer a variety of error functions. So we can use any one of them, or else we can write our own evaluation metric. So we can use any one of these. There are plenty of ways for doing it. Before that, I would like to say why evaluation is important. Evaluation is comparing the expected response with the system response to check how well our model is performing. We have seen examples for that. And there is a score, numerical score for quantifying the process. And that score is called as an error score. There are a lot of evaluation metrics. But this is all fine. But why evaluation is important? It is important for three reasons. The first reason is it ensures reliability. So it checks if the system performs consistently or not. For that purpose, evaluation is important. Second thing is it identifies weakness. So if the system makes some errors, we can analyze it and improve it. The third thing is it prevents harm. So if you look at the self-driving cars, it is moving when it was supposed to stop. So it's a critical error. So in critical applications like autonomous cars or in medicine, if any incorrect responses occur, then there is a serious consequence. So in order to avoid those serious consequences, it prevents harm. Evaluation prevents harm. So for this reason, we need a evaluation. Is it clear?
Yes, ma'am.
So next, so far we have seen about two steps in the learning process. One is a representation, other one is evaluation. Now we will learn the third process, which is called as optimization. So what is optimization means? If the system has not learned something perfectly, but it wants to improve, and that process is called as optimization. It is different from saying what is optimal or optimum. Optimal or optimum means it has already reached the ideal state in some context. Something which is at the optimum, we cannot improve it further. Something is in the process of improving, then it is called as optimization. So if the system hasn't learned something, plus it wants to improve, then this process is called as optimization. Is it clear? So let's take one example. So imagine we have a wet cloth to hang over a line. It is the simple and the optimal solution is to use cloth pins, and we can hang the wet clothes. They do not using cloth pins will not harm any clothes. But suppose imagine if you are using duct tape to attach the clothes to the line. This is not an optimal solution to use duct clothes. So what we can do, we can refine it by using, like, we can find a band of duct tape that is slightly less sticky so that it will not shred the clothes when we put in for hanging. Or else we can cut the strips in the lengthwise so they don't weigh so much and they can drag down the line. So what we are trying to do here is that we are optimizing a poor solution by making it better. So the poor solution is using the duct tape. The optimal solution is using cloth pins. So here we are, what we are doing, you are using a tape to hang the cloths. Using a tape to hang the cloths is poor solution. But what we are doing, we are trying to make it better. We are trying to make a poor solution work better. So this is called as optimization. Optimal solution is cloth. Other example could be finding a global minimum. So if you remember in the earlier class, we have studied about global minimum and local minimum. So global minimum means, so is an optimal solution. Finding the global minimum is the optimal solution. But what we are trying to do is that we are trying to get closer to the local minimum. So this is called as optimization. While reaching the optimal is usually preferred, but what we often do in machine learning is that we try to find out where is the local minimum. That way we are optimizing our solution. So the process of optimizing a learner. So we are optimizing a learner through an algorithm called as optimizer. So the process of optimizing a learner using an algorithm called optimizer. So whenever you hear the term optimizer, you know that it is an algorithm which is used for optimizing the process or a learner. So there are different optimizers available. In one of the class, we will learn the different optimizers available. So why do we have different optimizers? Why one solution cannot fit all means there is a theorem called as no free lunch theorem. So what this no free lunch theorem does is that it says no optimizer could ever be better than all others in all situations. So it is not a single optimizer will work for everything in all situations. So we need to choose a different optimizer for different purposes. So no free lunch theorem states no optimizer could ever be better than all others in all situations. So we need to pick the right representation for the right learner, and we need to pick the right optimizer so that we can learn better. So is it clear? So optimization means when the system has not learned something well and it wants to improve, and that process is called as optimization. And the algorithm which does the optimization is called as an optimizer. So optimal solution is an ideal solution. When the ideal solution is reached, we cannot improve further. But optimization, during the process of optimization, we continuously improve. No free lunch theorem states that no optimizer would ever be better than all others in all situations. So we need to choose the right representation and right optimizer for learning. Is it clear? Now we will, with one more concept in learning, we will go forward. This concept which we are going to learn is called as deduction and induction. So learning is an ability to turn the data into knowledge. Learning will convert data into knowledge. Suppose you have a raw data, you can convert this into a form of numbers, labels, strings, or descriptions or patterns or whatever it is, so that it makes sense to us. So learning can convert a raw data into the form which is useful to make sense. So most of the machine learning algorithm has two approaches of learning, and those two approaches are called as deduction and induction. So what does deduction means? It starts with a theory or a hypothesis, which makes predictions. So what is deduction? It is a process where we start with a theory or a hypothesis which makes predictions. So what we will do after that, we will gather evidence to see if the predictions are accurate or not. If the piece of evidence supports our theory, then we can refine our hypothesis. If the piece of evidence is not supporting our theory, then what we need to do is that we need to exclude the circumstances where it is not correct, and we have to narrow our predictions. So in other words, we can say if we have enough supporting data, then we have enough evidence for our theory. If we don't have enough evidence or enough supporting data, we need to abandon that hypothesis and then start a new search for a data, or else we have to refine our hypothesis. So this is what it is. So what does induction means? Unlike deduction, what here we do is that we make observations. We make observations and then we examine in a quest to find patterns. We make observations to find patterns in the data. So more observation we have, more likely that our patterns are to be present. So deduction and induction are two processes of learning in machine learning. Deduction means we will have a theory or a hypothesis to start with, and then we will make predictions using that. Induction means we will make observations. Here we don't have any prior assumptions, but we will make observations to find the patterns in the data. So more than observations which is present, then more likely are patterns to be. Is it clear? So far what we have seen is that we have seen the learning process in three types: representation, evaluation, and optimization. And we have also seen two general approaches of learning, uh, which is deduction and induction. Now we will, do you have any questions so far? If you don't have any questions, we will go to the next topic, classifiers. So anyone would like to, previously we have studied some principles about classifications. So anyone would like to throw a light on what you know about classification so that I will improve my learning. So we are in the process of optimization now. So we will learn, we will get to know what you know, and we will integrate new information to it. So anyone would like to tell what we know about classifiers? So what is a classifier? Anyone can comment on it?
Ma'am,
Yeah.
classifiers are a set of things which helps us divide our data into with their help, with their features, it helps to classify your data.
Mostly for categorical data, binary
Sorry.
classifiers. I mean, it's
Yeah,
used for
binary classifiers. We studied about binary classifiers. Yes.
yes, and for mostly for categorical data. It is applied for mostly for categorical data. Uh,
Okay.
mm,
Binary classifiers. I will note down what you are saying. Binary classifiers, categorical data. Then,
so the
so what is a
class
classifier essentially?
It's an algorithm which helps us categorizing data into groups so that it is easy for us to understand it.
Fantastic. Fantastic. Any more thoughts? Okay. So classifier is a major application in machine learning. It helps us to classify or categorize anything. It is not just limited to categorical data, even continuous data, it is applicable. It can classify images, sound, or any type of data. There are variety of binary classifier is one type. There are variety of popular algorithms used. So the major classification is supervised class algorithms and unsupervised algorithm. So supervised and unsupervised algorithms are used for classifying the data into different categories. So what we have done previously is that we have seen about binary classifier, multi-class binary classifiers, and the different techniques used in it. We have laid the foundation about classification work, but there are more to classification than just building and training and generic algorithm. There are more to it. So in today's class, we will see some of the examples, some of the types of classification, and we will also see, if time permits, we will also see some of the examples used in the classifier. So what we need to do, what is the key step in designing or training a good machine learning system? Anyone would like to tell? What is the key step in designing a machine learning system? It can be anything. Anyone would like to guess?
Select features by which we are going to
Okay,
classify.
selecting features. Any other thoughts? So what we need to do for selecting features, how you will select features?
PCA.
PCA. Okay. Anything else? So let's not talk in terms of algorithms. What do you think is intuitively essential for building a machine learning algorithm?
Right data, I mean, right inputs, training sets.
Fantastic. Right input. So I can tell us understanding the data. So we need to understand the data before we design or train a machine learning system. So we should usually look over the data, develop a feeling for it, and then we can match the design of our system or task at the hand. So let's give you an example. Suppose if you are having aerial photographs of different forms. So we want to classify the fields based on the crops which is growing there. So we have taken the aerial photographs of the forms. So how do we say that how many different types of crops are available in the photographs? How we can say we cannot quantify it as 5 or 25 unless we look into the data. We will not know actually how many different types of crops are there. So if you pick a few numbers, then we are limiting our answers. If you pick too many numbers, then we are providing unnecessary useless distinctions. So what we need to do is that we need to look into the data. When you look into the data, you will know how many types of crops are there. Then we can build a system based on that one. So we need to, before start building the system, we need to look into the data, get a sense of how many different categories are going to be detected or distinguished. Then we have to build our algorithm accordingly. So the great way to explore the data is to use many tools to see how specific our classification algorithm are going to be. So looking at the data is the first step in any algorithm. And then we will get a grasp of the data and we can build a thing. So in today's class, we will look only the 2D data and 2D classes for discussions. It is not that classifiers are meant only for 2D data and 2D classes. Two D data means it has only two features. The dimension refers to the number of features. So for all our discussions in this topic, we will limit to two classes and two features. Though it is capable of classifying multiple dimensions and multiple classes, we will keep it with only this. So these days with modern libraries, with just 2 lines of code, you can write any classifier. So we will see some of the classifiers in the tutorials also. But in today's class, we will briefly see the major classes, and also if time permits, we will see some of the examples in the classifier. So the types of classifier, previously you have seen binary classifier and multi-class classifier. So today you will see a different way of different types of classifiers. So different approach of categorizing a classifier. So there are two approaches. One is parametric approach and the other one is non-parametric approach. So what is a parametric or non-parametric classifier? These are the two broad categories of machine learning models used for the classification task. So the main key difference between these two is that how they learn from the data. And how they make predictions. So first we will see about parametric classifier. So in a parametric classifier, these models makes assumptions based on data distributions. It assumes the data follows a specific distribution and it learns from a fixed number of parameters. So what is the characteristic of a parametric classifier is that it learns from the parameters. So it has the name parametric classifier. So and also it assumes two important points to remember. The first point is that it assumes the data follows specific distribution. The second thing is that it learns from a finite set of parameters. So if the classifier learns from the finite set of parameters, it is called as parametric classifier. If it is not learning from a finite set of parameters, it is called as non-parametric classifiers. So the parametric classifiers also has one more characteristic that it assumes that the data follows certain distributions. So suppose if the distributions are not correct, if the distributions are incorrect, the model may not perform well. So the examples of parametric classifier are logistic regression, linear discriminant analysis, Bayes classifier, artificial neural network with fixed architecture. So the advantages of this method is that it works well for large data sets. Second, it is less prone to overfitting. The disadvantages is that the assumptions can be incorrect because we make assumptions about the distribution of the data. So the assumptions may be incorrect. Second, it may not be flexible with complex data. And it can have limited capacity with for nonlinear decision boundaries. So what we saw about the parametric classifier is that the data follows certain distribution. It learns from the finite set of parameters. There are some examples for it. The most common example is logistic regression. And there are some disadvantages and some advantages for this one. So now let's look into non-parametric classifier. So what I said, if it does not learn from, unlike this one, it does not assume any fixed distributions. Here, it assumes distribution. It learns from the parameters. Here, it does not learn from parameters. It does not assume any prior distribution about it. So it do not assume a fixed distribution. Nor it has some predefined set of parameters. But it learns directly from the data. So parametric classifiers learn from the set of parameters. Non-parametric classifiers learns directly from the data. So what happens when the data is increasing here, the number of parameters will grow. Here, the number of parameters will be fixed in the parametric classifier. Here in non-parametric classifier, what will happen when the data size is growing? Because since it is learning directly from the data, when the data size is growing, when the training data is growing, the number of parameters also will grow. And here we learned it is not flexible with complex data, but this one is flexible with complex data and non-linear patterns. Here it may be applicable only for linear patterns. This one will be applicable for non-linear patterns. So we will learn some examples for this one. So K nearest neighbor is an example of non-parametric classifier. Non-random forest. Support vector machines. So it is an example of non-parametric classifiers. Neural networks with adaptive architectures. Is an example of non-parametric classifiers. So we can write the advantages and disadvantages of this one. So the advantages of non-parametric classifier is that it makes no strong assumptions about the data. Second is that it can use complex models. It is flexible with complex models, works well with smaller data set. The disadvantages is it has since it is learning from the data, if it has a larger data set, then the inference is slow. But it is we saw that the parametric model is less prone to overfitting, but this is more prone to overfitting. It requires more data to generalize. So what we saw is that so far we have seen there is two approaches in the classifier. One is parametric approach, and another one is non-parametric approach. So the main thing with the parametric approach is that it has a strong assumption about the data, whereas non-parametric classifier does not have an assumption. The parameter size is fixed in the parametric classifier, whereas in the non-parametric classifier with the data, the parameter size grows. With the flexibility, it is parametric approach is less flexible. Non-parametric approach is highly flexible. Larger data sets can be used in the parametric approach because it is not going to learn from the data. It is going to learn only from the fixed parameters. So larger data sets are suitable for parametric approach, whereas complex and small data sets are suitable for the non-parametric approach. And we have seen the examples for both the classifiers. So when to use a parametric model and when to use a non-parametric model. So when we will use a parametric model, so when we have a large data set, we can use a parametric model. Or when we know the data follows certain distribution, we are sure that the data has some certain distribution, then in those instances, we can use parametric model. Suppose we need an interpretable model, then we can use parametric model. When to use a non-parametric model? So when we have a small or a complex data set, when we don't want to assume a fixed distribution, when we need flexibility to learn intricate decision boundaries. So during these instances, we will use a non-parametric model. Suppose we have the another one comparison is with the speed and the memory. So there is a trade-off between the speed and memory. So we know that the parametric classifier assumes the data distribution and it is storing the parameters. It is learning from the set of parameters. So it is, since it is learning from the fixed set of parameters, it does not need much memory. On the other hand, non-parametric classifiers save all the sample data. Their memory consumption goes up as we train. So more training sample it sees and stores. So the memory of the classifier will be high. So if we have larger memory, we can use non-parametric model. So we have to diligently choose which model classifier we are going to use. So imagine in your project, you are asked to develop a classification model. So based on your data, you need to first decide which model, which algorithm to choose. So whether you are going to choose a parametric classifier or a non-parametric classifier, based on these characteristics, you cannot randomly choose an algorithm for your problem. So you have to look into your data. Looking at the data is the first step. Look at the data, whether it is small data, large data, or a complex data. Identify the type of the data, and then choose your requirements, whether you have a lot of memory or a less memory, or what, if you know the distribution of the data, or do not know the distribution of the data. So you have to find all these details and information, and then you decide which algorithm you are going to apply. You cannot straightforwardly take an algorithm. You should have a justification for choosing an algorithm based on these steps. So what we have done in this class is that so we have started with the classifier. So the types of classification approaches, parametric approach and non-parametric approach. So how they are majorly classified is like, so based on what they learn from the data and how they make the predictions, these two approaches can be differentiated. So we saw about the parametric classifier, when it can be used. We saw the examples of it. We saw the advantages and the disadvantages of it. And we also saw when we can apply non-parametric classifier, what is a non-parametric classifier, and we have seen the examples of it, advantages and disadvantages of that one. So is it clear? Any questions? So if you have no questions, we will meet in the next class. Next class is on Monday. Thank you, everyone.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.